So we are going swimming?
Yes, let's wait for the pool to get free.
Ouch!
Haha! Did you know that Archimedes, a Greek scientist, went through a similar experience? While most of us have heard the story where Archimedes ran through the streets yelling, "Eureka!" The real problem he was struggling with at that time is not so well known. According to a famous Roman writer, a new crown had been made for King Hydrometer, and Archimedes had to determine whether it was of pure gold. The king wanted reassurance that no silver had been added to the crown by a dishonest goldsmith. To do this, Archimedes needed to find a method to determine the volume of an object with an irregular shape. In this lesson, you will learn how Archimedes solved this problem and propounded the Archimedes principle. You will also learn about buoyancy and flotation of objects. At the end of this lesson, you will be able to explain Archimedes' principle and its applications, define relative density, explain the applications of relative density, apply the formula of relative density to calculate the density of a given substance, define buoyancy, and explain the phenomenon of flotation and sinking using the concept of buoyancy.
So, how did Archimedes solve the problem? And what did water have to do with it?
While taking a bath, Archimedes noticed that the level of water in his tub rose as he got in. He realized that he could use this effect to determine the volume of the king's crown. The submerged crown would displace an amount of water equal to its own volume. Based on this, he eventually propounded the Archimedes principle. This principle states that when a body is immersed completely or partially in a fluid, it experiences an upward force that is equal to the weight of the fluid displaced by it. We can verify Archimedes' principle through an experiment. From a spring balance, suspend a small block of iron weighing W1, say 700 grams. Take an overflow jar and fill it with water until it is on the verge of overflowing. Under the spout of the overflow jar, place an empty beaker that weighs W2, say 150 grams. Gently lower the iron block suspended from the spring balance into the overflow jar till the block is completely immersed in water. The water overflows into the empty beaker placed under the spout of the overflow jar. Now, note the weight of the iron block in water as well as the beaker with the displaced water. The weight of the iron block in water, say W3, is 600 grams. The weight of the beaker, say W4, is 250 grams. Thus, there is an apparent loss in the weight of the iron block. The apparent loss of weight of the block is equal to W1 minus W3. This is equal to 100 grams. The weight of the water displaced is equal to W4 minus W2. This equals 100 grams. You can see that W1 minus W3 is equal to W4 minus W2. Thus, this verifies that the difference of weight of the iron block inside and outside the water is equal to the weight of water displaced into the beaker.
So, once Archimedes had determined the volume of the crown, he could find out whether or not it was made of pure gold.
That's right. Remember, mass of an object is a product of density and volume. So, knowing the density of gold and the volume of the crown, Archimedes could perform the necessary calculations to solve the problem. The Archimedes principle finds many applications in our lives. One of these applications is determining the density of a given liquid using an instrument called a hydrometer. A hydrometer is generally made of glass. It consists of a cylindrical stem and a bulb. The bulb contains a mercury or lead shot to make it heavy. This ensures that the hydrometer floats upright in the liquid. To determine the density of a liquid, it is poured into a tall jar, and a hydrometer is lowered gently into the jar to float freely on the liquid. The hydrometer reading gives the density of the liquid. For example, if we place the hydrometer in a jar of carbon tetrachloride, the hydrometer shows a reading of 1.6. Thus, the density of carbon tetrachloride is 1.6 gram per centimeter cube. As you know, the density of a substance is the mass of a unit volume of that substance. The density of a given substance under specified conditions remains the same and is one of its characteristic properties. However, sometimes it is more convenient to use another measure called relative density. The relative density of a substance is typically referred to as the ratio of density of the substance to the density of water. It indicates how heavy or light that substance is when compared to water. For laypersons, the concept of relative density may be easier to understand than density. For example, if we state the density of iridium as 22,650 kg per meter cube, not everyone may easily grasp how heavy iridium really is. However, if we say iridium is over 22 times as dense as water, the number gives us a realistic idea of weight of the unit volume of iridium. As a more common example, the relative density of silver is 10.5. This means silver is 10.5 times as heavy as water. Since the relative density is a ratio of similar quantities, it has no unit. However, while calculating the relative density of a substance, care should be taken that densities of the substance and water are expressed in the same system of units. The concept of relative density finds many applications, especially calculation of the densities of given liquids. For example, a lactometer is used to test the purity of milk on the basis of its relative density. An alcohol meter uses the concept of relative density to determine the alcoholic strength of a liquid. Similarly, a saccharometer is used in determining the amount of sugar in a solution. The formula for relative density of a given substance is relative density is equal to density of a substance divided by density of water. Given the relative density of a substance, you can use this formula to determine the density of that substance. For example, the relative density of carbon tetrachloride is 1.6. To calculate its density, let's substitute the given values in the formula. Relative density of carbon tetrachloride is equal to density of carbon tetrachloride divided by density of water. 1.6 is equal to density of carbon tetrachloride divided by 1 gram per cubic centimeter. Density of carbon tetrachloride is equal to 1.6 into 1 gram per cubic centimeter. Therefore, the density of carbon tetrachloride in CGS system is equal to 1.6 gram per cubic centimeter. Now let's look at another aspect of Archimedes' principle, which explains the concept of floating and sinking, also known as buoyancy. As Archimedes' principle mentions, when a body is immersed completely or partially in a fluid, it experiences an upward force. The upward force exerted by a fluid on any object is called upthrust, the buoyant force, or simply buoyancy. The concept of buoyancy explains why certain objects float on water while others sink. All objects experience buoyant force when immersed in water. Floating and sinking of objects depends on how the density of the object compares with the density of water. An experiment will help illustrate this concept. First, we take a beaker filled with water. Find two identical coins, one of metal and the other of plastic. Place both the coins on the surface of the water. The density of water is 1 gram per cubic centimeter. The density of iron is 7 gram per cubic centimeter. The density of plastic is 0.8 gram per cubic centimeter. The plastic coin floats and the metal coin sinks.
So how can we determine whether the buoyant force on an object will exceed its weight?
The magnitude of this buoyant force depends on the density of the fluid. Therefore, the floating and sinking of objects depends on how the density of the object compares with the density of water. The plastic coin floats in water because the density of the plastic coin is less than the density of water. Therefore, the upthrust of water on the plastic coin is greater than the net weight of the coin. On the other hand, the iron coin sinks because the density of the iron coin is higher than the density of water. Therefore, the upthrust of water on the metal coin is not able to overcome the net weight of the coin. Thus, according to the principle of buoyancy, objects with a density less than that of a given liquid float on that liquid. Objects with a density greater than a given liquid sink when placed in that liquid.
That's cool. But wait a minute. The density of iron is greater than that of water. So how is it that if we drop a piece of iron in water, it sinks? But our ships are built of iron and steel parts, and they don't seem to have any problem staying afloat in water.
That's a good question. To better understand why a ship floats, let's look at a very simple everyday example of buoyancy. Take an empty glass bottle and close its cap airtight. Put the bottle in a bucket filled with water. Then, try to immerse the bottle in water. You'll observe that attempts to push the bottle down in the bucket are unsuccessful, and the bottle floats on water, even though the density of glass is higher than that of water. Here's the reason why. The bottle contains air inside it. The volume of the bottle includes the volume of air in it. The density of air is much less than that of water. This means that the overall density of the bottle becomes lower than that of water. Hence, the upthrust on the bottle is greater than the weight of the bottle. Due to this, the empty airtight bottle is pushed upward when we try to immerse it completely in water. Therefore, the glass bottle floats on water, In order to make the bottle immerse completely in water, the volume of water equivalent to that of the bottle must be displaced. Note, to keep the bottle completely immersed, the upward force on the bottle due to water must be balanced. This can be achieved by an externally applied force acting downwards. This force must at least be equal to the difference between the upward force and the weight of the bottle. The reason for flotation of the ship is similar to that of the flotation of the glass bottle. Even though the density of iron is more than that of water, the ship does not sink. The total volume of the ship includes the volume of the air in it and the volume of the metal. This reduces the overall density of the ship to a value much less than the density of water. Hence, the ship does not sink.